Hey science fans, so we've done ionic bonding. It's time we spoke about covalent. The definition of a covalent bond is a shared pair of electrons. It does occur between two nonmetals, so they're on that side of the periodic table. I should do my own sound effects. It occurs between two nonmetals and it's where they share electrons so that they have a full outer shell. You can have double bonds, which is where they share two pairs of electrons, triple bonds where they share three pairs of electrons, and in your exam you need to be able to draw them. That's normally worth 2 to 3 marks. And you also need to know the properties of the simple molecular, so like water, carbon dioxide, but also of the giant structural ones like diamond, graphite, graphene, and the other one, silicon dioxide. Better get going. It's all bonding.
About what a covalent bond is, it means a shared pair of electrons. Atoms want to share electrons so that they can have a full outer shell. So if we look at something like hydrogen, it's got one electron in its outer shell. That's not a happy hydrogen. But what he could do is share that electron with another hydrogen. See how happy he is now? That's because he's now got 2 electrons in this shell. He's got 2 electrons in the shell and they're just sharing them so they join together. I mean, it could happen in a larger atoms that could join together. So for example, chlorine's in group 7. Chlorine has got 7 electrons in its outer shell. Not got a full outer shell, needs 8 to have a full outer shell. So if my little friend chlorine was to react with my little friend hydrogen over here, that's a terrible diagram. We've got HCl. So we've got hydrochloric acid here. He's now got a full outer shell. He's got a full outer shell. Don't know why they're all male. Sorry about that. So they are now bonded together. This bond, this particular bond, is very strong. This is the covalent bond right here. For the 3 marks in the exam, you get 1 mark for showing dots and crosses in the right places and 1 mark for showing that they are sharing their electrons in the right places. The covalent bonding gives rise to 2 types of covalent structures. When we spoke ionic, we really only spoke about lattices, but we have simple molecular. Now, simple molecular are things like little molecules like water, methane, hydrochloric acid, carbon dioxide, hydrogen as a diatomic molecule, chlorine as a diatomic molecule. So these, you have to know the properties of these based on like how they're bonded, and you also need to know the properties of giant covalent compounds. These are things like diamond, graphite, and silicon dioxide. Let's get cracking. Look at the properties of all of these bad boys.
Bonjour. So what we're going to do is we're going to look at the properties of simple molecular molecules. These are the little ones, okay, and they're generally all liquids or all gases. Okay, so I'm going to look at the properties of water and we're going to attribute that to the bonding within them, okay? So if I've got a usual water molecule, it will look like Mickey Mouse. Oxygen is the larger one. Oxygen has 6 electrons in its outer shell. I've drawn all 6. Hydrogen has 1. So they're going to share these. So this now has 2 electrons. This has 2 electrons. Very happy hydrogens. And this now has 8. Very happy oxygen. That is 1 water molecule. Now, something we know about water is it has a low boiling point and a low melting point. Okay. I'm just going to draw some smaller molecules so you can see. Now, the reason that it has the property of a low melting point or a low boiling point, it's not got anything to do with breaking the covalent bonds. Breaking covalent bonds is really, really tough. It's really hard work. They are really, 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 really strong. However, the boiling points are really low because each molecule has this force holding them together, which is why water flows, and we have to input energy into that to separate the water molecules apart. Okay, and the reason why it doesn't take much heat energy to break them apart is for this sentence. You need to learn this sentence. They have weak intermolecular forces. So when we heat up water, we are not breaking hydrogen from oxygen. We're not breaking up this beautiful bond here. We're just separating the molecules from one another. So you've got water as a gas everywhere. I'm a bit everywhere, a bit gassy everywhere. So these are the key things. They have low melting and boiling points,
weak intermolecular forces, and they don't conduct because they have no free moving electrons and no free moving ions. They can't do that. Those are the properties of simple molecular. I realise that I've just cut that off the bottom. There it is. They don't conduct. Okay, let's move on to giant. So we're going to move on to the giant ones, but I've had to draw these in advance because I'm terrible at drawing them. So the two main ones that you need to know are both allotropes of carbon. So they're both different forms of carbon in the way carbon bonds, and they are both solid at room temperature. Let's hope the English department does not see this. Okay, so key things to know about these. They're both solid at room temperature. They both have high melting points and high boiling points because the covalent bonds, the bonds between the carbons, are very strong, which means they need lots of heat energy to break, going off the bottom there, to break the bonds. Okay, you need to know the properties of these two allotropes and also silicon dioxide, but I'm just going to focus on these two now. Now, diamond is very, very strong. It's one of the strongest materials on Earth, which is why we use it for drill bits. And the reason why it's so strong is because it has these carbon covalent bonds. And I said that covalent bonds are really, really, really strong. And each carbon molecule is bonded to 4 other carbons. So each carbon atom has 4 carbon bonds. If we look at carbon in terms of its electron structure, it has 4 electrons in its outer shell, which means that it can bond onto 4 other carbons, which means it creates this really strong network of 4 carbon bonds. Now, there are no free moving electrons, no free moving ions, so it cannot conduct, but it means that it is a really, really strong, tough. And the way it's made is literally by huge amounts of heat and pressure, forcing them together. So let's look at the properties of graphite now. Now, graphite, believe it or not, these are hexagon shapes of carbon joined together, and they are found in layers. The layers can slide over one another, which makes it really useful for pencils, but also as lubricants because it's slidey, which means it is much softer than diamond, although those bonds are really strong, so it still has a really high melting and boiling point. Now, in graphite, the main difference is each carbon is bonded to 3 other carbons. Now, if you remember from our diagram here, this means that for every carbon that is joined to 3 other carbons, there's 1 free moving electron, which when you've got a lot of carbon atoms is a lot of delocalized electrons, which means they can conduct electricity. Woohoo! Okay, which is why graphite is quite often used when we do electrolysis, because it conducts electricity really easily due to these free moving delocalized electrons. For triple, you need to know about 1 layer of graphite, which is graphene, and again conducts electricity, so it's really good for using as like phone screens, things like that. That's it. That's all of the properties. We're done. You need to know how to draw covalent bonds. You need to be able to define them, share a pair of electrons. That's easy. And you need to be able to give properties of simple molecular, low boiling points because they have weak intermolecular forces. And you need to be able to give properties of at least 2 giant covalent ones. So high boiling points, high melting points, and why? 3 carbon bonds, 4 carbon bonds. That's it. Boom. Done.